A very great pleasure and an honor to be giving this lecture. I'm a real Fisher fan, although I suspect that if I'd known him in real life, I might have found him to be a rather difficult character to get on with. So, first of all, some acknowledgements. Thanks to the Trust, also to various people who've helped me, various papers, and in particular, John Aldrich and Andy Grieve have made very helpful comments on an early version of this talk, and to say that some of this work is supported by a European Union grant that I have. An apology to all of you. The abstract promised an awful lot. I was going to cover the whole of the history of p-values, and that would start with John Arbuthnot, a Scot, back in 1710, or possibly with Daniel Bernoulli, a Swiss, and continue to 2017. But in fact, I'm going to limit myself to just about 10% of this. But if you take what I promised as being the null hypothesis, 10% is not statistically significant, and so I haven't rejected my promise. So on that basis, I'm going to carry on. And I shall actually salve my conscience by pretentiously sprinkling in a few names as I go along. And I have various excuses for that, but the best is this lecture stands between you and a drink. And that is very worrying for any particular lecturer. So, an apology also to Bayesians. I'm going to say a few harsh things about Bayesian statistics, but not about statistics in itself, simply about a particular criticism of Fisher which Bayesians make. And I'm firmly convinced that really what's happening is a sort of proxy war. It's really a war between different schools of Bayesian statistics. They don't necessarily have to be at war, but I think they are in a sense. And in the middle are somehow p-values. And when you look at the history of p-values, you'll see why this is so. So I'm going to start with a case against Fisher. So here we have Fisher, the cause of inferential confusion, and Robert Matthews is a very interesting person. He is not only a journalist, but he's a physicist and he's a statistician, and as I often say, the intersection of those three sets surely only has one individual in it, so he is actually sui generis. Ronald Fisher gave scientists a mathematical machine for turning baloney into breakthroughs and flukes into funding. And you may say, well, that's pretty amazing. Where did that appear? Well, it appeared in all places in the Sunday Telegraph. And if the Sunday Telegraph knew as long ago as 1998 that p-values were a busted flush, why on earth are we still talking about them? Here, in fact, he's quoted by David Cahoon, a fellow of the Royal Society, who recently, very, very late in his life, has become converted to looking at p-values in a Bayesian way, although he can't bring himself to utter the B word. And so he sort of says he's not really a Bayesian, and he doesn't understand what Bayesians run about. But anyway, not the only one. Here's Francis Anscombe, who was a very great statistician himself, who says this: results of clinical experiments often culminate in a significance test. It is natural to suppose that well-established statistical theory supports such tests. This is not so. Significance tests of such null hypotheses at the end of an experiment can fairly be laid at R.A. Fisher's door, especially because of his insistence of them in the design of experiments. So a particular book that Fisher wrote that was very important, though actually myself I would have said statistical methods for research workers perhaps deserve more of the blame. And here we have Fisher, the false and plagiarizing prophet. Ziliak and McCloskey. Ziliak is a statistician who has at least one good thing going for him. His first name is Stephen. Here he says that student of student's t-test was right and his difficult friend Ronald A. Fisher, though a genius, was wrong. And then they want to essentially convince you that all of Fisher's vast inferential machinery was a terrible mistake. So, this is the false history that I'm going to claim is what people are saying I'm going to claim is false. To the extent that scientists were using formal inference before Fisher came along, they were using something that we would now call Bayesian, although the word was not actually used. They were dealing with what was sometimes called inverse probability. R.A. Fisher invented p-values as part of his rival system of frequentist statistics, and they gave statistics much more easily. This is the breakthrough baloney machine that Robert Matthews referred to. Somehow, Fisher made it easier for them to claim, Eureka, I found something important. So they became an instant hit, and they seduced scientists away from the path of Bayesian rectitude, and this is largely responsible for a replication crisis that we now face. People publish one thing, people try and repeat it. Well, not very often, but if they do, then what they find is it doesn't repeat. And so the question is, what is the cause of all this? But the history is not like that. It's not true, in my opinion. P-values may or may not be good statistics. I'm not going to claim that they're a particularly brilliant way to look at things. But what I also think is that setting the historical record straight will help us to see what the problem is. But the bad news is we're nowhere near a resolution. We are not, in fact, I think, in the near future, going to find some automatic system of inference or even a theory that everybody can sign up to. But I'm also well aware that the problems we face will have to be solved by better brains than mine. So let's go back to Gossett. This is the person that Ziliak and McCluskey said was the true inventor of modern statistics. He was actually born in Kent. He was educated at Winchester and Oxford. He got a first in mathematical moderations and a first in a degree in chemistry. And unusually, for someone who was a leading figure in statistics, he was educated at that time. He was educated at Oxford. I think I fear that, having said that, that our own president may have been educated at Oxford originally. So I don't wish to cast aspersions on that particular place. But traditionally, what happened was statisticians were educated in Cambridge, and they then went to work at UCL. And I put that like this: the reason was that only Cambridge was good enough for statistics, but statistics wasn't quite good enough for Cambridge. And so basically statisticians were forced to go off there. But Gossett is an exception, and he went to work, of all places, he went to work with Guinness in Dublin. And Guinness at the time had a very enlightened policy of getting scientists to go out and interact with the academic world, and they gave him a year's leave of absence to go and work with the leading statistician at the time, who was Karl Pearson. And during that time there, he published a paper called The Probable Error of a Mean in Biometrica, which we regard as being the original of the t-test. And this is the paper here. It's divided into the following 9 sections. I'm not going to go through all of this, but I'm going to go through an instance of their use, which appears in the table, because that particular calculation that the student made was also repeated in a slightly different way in Fisher, and that will help us to understand what's going on. So these are, in fact, the original data that student used. He used data from Arthur Cushney, who was a physiologist who was born in Fochabers, which is a town on the Moray Firth. And he then went to study in Bern and Strasbourg and was appointed at only the age of 27 as the professor of materia medica, which is essentially the professor of pharmacology at Ann Arbor University in Michigan. So at the age of 27 only, and he worked a lot on optical isomerism. And together with a student of his, Alvin Peebles, they published this paper in 1905 in the Physiology Journal. And what they had done was they compared the number of hours of sleep gained for a number of inmates at the insane asylum at Kalamazoo to see how much extra they slept if they were given these various treatments. By the way, they had in fact tested these treatments on themselves. So they were not using the inmates as guinea pigs without having, first of all, checked that the stuff was safe, but these are their figures. So these are the figures as reproduced by student. Actually, student copies down the data incorrectly. So it's not, in fact, a comparison of dextro and levo form. It was a comparison of the racemate and the levo form, so the mixture of the right-hand and left-hand form, and they were trying to infer the difference between the two forms by comparing the mixture to the pure form. And in any case, he also got down a different drug altogether. But anyway, student finds these particular differences here. You'll notice that all the differences, with the exception of one, are positive. So it seems to be the case that the particular inmates are sleeping rather longer when given the left-hand form than when given what student assumed was, in fact, the right-hand form. And what student says is, and this is the interesting thing, he does an analysis, and then he says, of course, the odds are about 666 to 1 that 2 is the better soporific. So immediately, he doesn't do a modern frequentist calculation. He essentially tells us something about the true value of the drugs. In a sense, he's saying something about various hypotheses, and he's claiming here that the odds are 666 to 1 that 2 is the better soporific, that the levo form is better than the dextro form, as he thinks. And odds of this kind make it almost certain that 2 is the better soporific, and in practical life, such a high probability is in most matters considered as a certainty. So here we have someone who's essentially using a Bayesian argument, in what sense I'll explain in a minute, who considers that a particular probability of this sort of nature is proof positive that one form is better than another. What student did not do, what he did and did not do, first of all, he obtained the distribution of the sample standard deviation. That was necessary for him to do this. He showed it was uncorrelated with the sample mean. That was also necessary for him to develop his particular statistic. He obtained the distribution of the ratio of the mean, assuming independence, and through a rather indirect argument. He went to an enormous amount of work working with a machine calculator, a hand-driven calculator, to tabulate this distribution. He carried out various empirical investigations. He also did some simulated some numbers. He applied it, and he interpreted the probabilities in a Bayesian way. What he did not do was he didn't show that the sample mean and variance were independent. He didn't generalize the problem beyond one sample. He didn't define the t-statistic in its modern form. That's actually due to Fisher. He did not use the modern significance test interpretation, and he did not explicitly use Bayes' theorem or any derivation that we would now call Bayesian during the actual calculations that he did. The extent to which he's a Bayesian comes from this statement only within the paper. The usual method of determining the probability that the mean of the population lies within a given distance of the mean of the sample is to assume a normal distribution about the mean of the sample with a standard deviation equal to S over root n, where S is the standard deviation of the sample, and to use the tables of the probability integral. So he doesn't really say anything about why this can be justified in a Bayesian sense, but he does claim that some sort of a Bayesian statement can be delivered, or what we would now call a Bayesian statement. More explicit reference to prior distributions is provided in his correlation coefficient paper, and I'm grateful to Andy Grieve for pointing this out to me. So in another paper in the same journal, he does use a more explicit Bayesian approach. Now compare Student and Fisher. What Student says, this 666 to 1 figure I've already noted. Fisher uses another argument. He says, let's assume that the two treatments are identical. Then, in that case, only one value in 100 of the statistic calculated will exceed this value. In other words, what he's saying is, if you believe that these two treatments are identical, then the result that has just been seen is a very, very strange and unusual result. He uses an indirect argument. He doesn't directly tell you what the probability is that 2 is in fact better than 1. So, if we look at Student's analyses, in fact, he compares 3 different analyses, but let's just have a look at the one we've been talking about so far. Odds of 666 to 1, that's the figure he concentrates on. What Fisher does instead is he calculates the probability of observing a result as extreme or more extreme. Well, in fact, he doesn't calculate it completely. He just says it's no more than 1 in 100. And why does he do that? Because in doing that, it obviates the necessity to be involved in more complicated calculations. What he did was he provided you with the 1 in 100 tables. You simply had to compare it to this table to see whether the statistic was larger or smaller than you would get. And these are, in fact, the critical values of t. The value of t that you need to have a look if you're going to do a one-sided test, we would now call 2.821, and two-sided would be 3.250. This is the value that we would use. So what did Fisher do? He reformulated the statistic so that asymptotically it's normal 0.1. Students' tables didn't have that effect. They weren't going anywhere interesting, but in fact, Fisher's table go towards the normal distribution, the distribution that was being used for large samples already by everybody before Student came along. He showed how it could be extended to other cases. He showed you could use it for 2 samples. He showed you could use it for regression coefficients. He generalized it to 3 or more means. He stressed an alternative interpretation, the one we now use, but they could actually also be found in Karl Pearson's work. And he suggested a doubling. He said you really should double it because you didn't know beforehand that you were going to find that the left-hand form was better than the right-hand form. It could have been the other way around, and you really ought to pay some sort of penalty for that. And so what he did was he proposed a doubling. In fact, what he did not do is he didn't actually calculate the p-value. He didn't calculate it here. He merely said it's significant at the 1% level. Funnily enough, he does calculate the p-value for the sign test. He notes that the values are significant. They're all in one direction. 1/2 to the power of 9 is 1/512, and he tells you this particular figure. If students had modern resources, this is what he would have calculated for his tail area probability. The 666 corresponds to p one-sided of 0.014. And had Fisher been able to use a calculation at the flick of a switch or the press of a button, as we now do nowadays, or the click of a mouse, I should say, then in that case what he would have got is he would have got a value of 0.028, and this is simply twice the value that student got. The only difference between them would have been that the probability would have been doubled. That's the only difference, but the point to remember is that student's interpretation is orthodox Bayesian, or at least what we would now call Bayesian, according to one particular model at that particular time point. A diversion here, by the way, is you'll sometimes find this mysterious thing, especially in America, referred to as NHST. NHST is null hypothesis significance testing. It's regarded as being a ghastly hybrid between a system due to Fisher and one due to Neyman and Pearson. Confusingly, the Pearson in question is not Karl Pearson, but his son Egon Pearson, who collaborated with Jerzy Neyman, a prominent Polish mathematician, in the 1930s to develop Fisher's approach further. And this is what Steve Goodman, writing in Statistics in Medicine, says: in an NP hypothesis test, there is no formal role for a p-value, and we're supposed to accept or reject the null hypothesis depending on whether the observation falls into a critical region defined by the study's design and the pretrial alpha and beta errors. The precise location of the observation within the critical region, as indicated by an exact p-value, is not relevant. So he's actually claiming there's a fundamental difference between Fisher's approach and Neyman's approach, but we now have an unholy mess in which these two things are mixed together, and the first thing any biologist does in writing out a plan, if they do write a plan for statistical analysis, is to say the significance level will be set at 5%, and then what they do is they calculate some p-values and they compare these p-values to 0.05 or not. If they are less than 0.05, then the champagne is broken open. If they are greater than 0.05, then some serious critical thought is given as to how possibly they could be nudged into the right direction. And if that doesn't happen, instead something is written like this: with a p-value of 0.08, one might write, the results showed a trend towards significance. And this, I often say, this is the wonder of having a medical colleague. This is the sort of thing they can do a statistician couldn't do. They know where the p-values are going, whereas we regard them as being already in a particular place. They either are or they aren't, but they know that with only more data, they would go in that direction, which just goes to show that they obviously have some form of clairvoyance. So, but actually this is not true. This distinction is completely false. No less a person than Lehmann, who was an avid disciple of Jerzy Neyman's, says that the value of a p-value is it enables others to reach a verdict based on the significance level of their choice. So you can imagine it like this. Pearson writes to Neyman saying, "My dear Neyman, result significant." And Neyman says to Pearson, "My dear Pearson, this is no good because I know you always use the 5% level and I always use the 1% level. How am I to determine that a result which is significant for you is significant for me?" And vice versa. So in fact, Neyman can say to Pearson, "My dear Pearson, result not significant," and Pearson says, "Well, how do I know it wouldn't be significant for me?" Eventually, they will stumble upon the idea that what they need to do is to quote the p-value, even though they are hypothesis testing. And you'll find this in Statistical Hypotheses by Eric Lehmann. So, Here's a diagram explaining, if you like, how students saw it. What he thinks he's done, once he's calculated all of this, he's produced a Bayesian posterior distribution. The probability is somehow centered on the point estimate. This is the mean difference in hours of sleep. And he's following Laplace via Airy, who was a particular astronomer come mathematician of the day that everybody read when they wanted to know how to calculate things with errors involved. And the distribution is centered on the statistic. And it's a statement about the probability of the parameter. But if you look at Fisher, he looks at it rather differently. As far as he's concerned, he's going to play devil's advocate. He's going to say, supposing there is no difference between them. Now let's have a look how the statistic would vary given that there were no difference. And so he's interested in this particular tail here. This is the value of 1.5, the difference of about 1.5 between the two racemates, the two isomers, not the racemate, two isomers that there are. And this here is the critical value, and he just notes it's beyond that, and that's this is the one corresponding to 1%. If I put the two diagrams together, then this is what they would look like. The blue one here is Fisher's curve, and the red one here is student's curve. And what they could do is they could calculate two probabilities which exactly agree. And I'll show you that by actually magnifying the diagram here. This is a probability that the left-hand form is in fact worse than what a student thinks is the right-hand form after all, and this is the one-tailed p-value. And these two particular areas are exactly the same. So the point is, numerically, student and Fisher do not have to disagree, and the only extent to which they would disagree is that Fisher would produce a more conservative inference by doubling the tail. Here, by the way, is a geometric way that Fisher looked at the t-test. He said, supposing we just knew how variable the data were, then in that case, we could see how unusual a particular result was. And here I've taken a rather degenerate case in which we have only two observations, because geometry is notoriously easier to see when you only have two dimensions than anything else, and I certainly can't follow Fisher in his inferential insights. And here we have the point of 0, 0, the first observation, the first poor patient who was given this optical isomers, and we tested the difference between the hours of sleep on one occasion and another. And the second one here, and these are two particular results. We have a sample size 2, and we can plot all of these results. Here are some simulations, by the way, that I've done. Everybody seems to love simulations these days. These are the boundaries that will be critical. I've actually chosen a 10% region simply because it's easier to see what's going on. And all the red points are samples that would lead us to believe that the mean was not, in fact, round about 0. This is the value we should see if there was no difference between the two isomers. This is the situation if there is, in fact, a big difference. We then expect all the points to go off in one particular area, and the statistical test would enable us to say now that many, many more occasions are significant. So many more experiments that we could do here with two individuals only would actually cause us to believe that the result was significant. Unfortunately, the contours of this particular diagram are not known to us. They're known to me because I'm the god of this universe. I created this simulation. I know exactly what everything is, but they're not known in general to anybody else. So what can we do? And this is where Fisher shows that there's a very cunning geometrical construction you could do. He says, supposing what I do is I simply cut a slice into the center of the cake. This particular slice will cover 10% of the cake altogether. That's what I propose to do, or whatever percentage I've chosen here. I'm a bit doubtful as to whether this is 10% now, but anyway, whatever it is. You can fix a certain slice that you cut, and you don't need to know the density in question. The cake can be dense at the middle and not so dense at the outside. You'll still end up in choosing exactly a particular percentage of the cake. And this is what you see when the points go off in the other direction. Because you don't know about the contours of the cake, you suffer a loss you more often mistakenly classify points as being not significant, only the red ones are significant, but nevertheless, you have a method of guaranteeing that you won't claim significance more often than you should do if the null hypothesis is true, and you still have a way of claiming it rather more often if the null hypothesis is not true. This, by the way, is very easy to demonstrate algebraically, but in preparing this lecture, I remembered the warning of the wise Chinese sage Confucius, not to be confused with Confucius. And Confucius warns any lecturer, if you commit algebra, you will suffer an aftermath. That's a joke, by the way. So, to sum up, Fisher and student did not disagree as regards probabilities numerically, at least not in any way that casts Fisher as more liberal. We've also got the whole business of the two-tailed controversy. I don't want to go into that. But they differed as regards interpreting the probability. And Fisher saw that any Bayesian interpretation depended on particular prior assumptions. Students simply used the default argument. The reason that students' paper was only influential, eventually influential is thanks to Fisher. So I just want to take this opportunity to reject Ziliak and McCluskey's claim that Fisher was merely derivative here and not very helpfully so. So who did produce a formal Bayesian derivation of the t-distribution? Well, Stephen Stiegler, another gentleman with an excellent first name, he has a law of eponymy, which basically says that if anything is named after somebody, they definitely did not discover it. And at the end of this wonderful paper, he reveals that, of course, Stiegler's law of eponymy was not discovered by Stephen Stiegler. It was discovered by Robert Newcomb. But we all know of it now as Stiegler's law of eponymy, and that just justifies what he says. But who, in fact, discovered the t-distribution? Well, definitely Jakob Lürup back in 1874. John Aldrich has been suggesting to me that Dedekind was possibly there before in 1860, Edgeworth again in 1883, Burnside independently in 1923, but by then Fisher was on the case, Jeffreys again in 1931, and of course he did it in his book of 1939. But Jeffreys is a Bayesian, and he uses a formal Bayesian argument all the way to produce this particular test. So I'm now going to carry on and consider the story with Jeffreys. And this is the point at which I get to sprinkle lots of names pretentiously. You will see here we have Laplace, Marquis de Laplace, who was a French mathematician, eventually appointed by Napoleon to be the Minister of Interior Affairs, an expert on calculus, and Napoleon dismissed him, saying that he carried into the business of government a love for the infinitely small. And so apparently didn't turn out to be a great administrator. But he was made a baron by Napoleon. That just didn't stop him actually helping to convict Napoleon in absentia when he was finally dethroned as emperor. De Morgan, 1838, who was one of the first people to work at University College London. But here, this is Venn of Venn diagram fame, and a great critic of Bayesian reasoning, and he introduces this particular formula based on a reasoning of Laplace. Imagine that you have a number of counters in a bag, and so far you've drawn them out, you've pulled out counters without looking inside the bag, having shaken the bag up very, very thoroughly, and you've pulled them out, and what you found is you found that all of the counters so far, let's say, are white. You are to imagine that so far, before you even started imaginary device, you saw one counter that was white and one counter that was not, and your estimate of the probability that the next counter pulled out will be white is the ratio of the total counters you've seen so far that are white plus 1 to the total counters that have been pulled out plus 2. Thus far, mathematics, as Venn says. Laplace, for instance, has pointed out at the date of the writing of his Essai philosophique, the odds in favor of the sun's rising again on the old assumption as to the age of the world were 1,826,214 to 1. This is assuming you've been around to see it rise all that time. De Morgan says that a man who's standing on the banks of a river has seen 10 ships pass by with flags, should judge it to be 11 to 1 that the next ship will also carry a flag. So this is the sort of reasoning that went on in those days. But a particular philosopher at Cambridge, Charlie Broad, pointed out that there was a great problem. And Broad is a very interesting person because he turns out to be a scientific skeptic who believed in extrasensory perception. So some of his particular research was psychic research, and he was a Knightsbridge professor of philosophy eventually. But in 1918, he published a bit of a bombshell, and it went like this. He said, that's fine, but if you think this is an argument for proving scientific laws, there's a problem. Because what Laplace has given us is he's given us a rule for proving that the next counter, giving us the probability that the next counter drawn will be white. But if we want to prove a scientific law, we're making a statement about something which always happens, and that's equivalent to saying all future counters will be white. And it turns out, using exactly the same argument, that although it is correct that the probability that the next counter that will be drawn will be white is large, given that they all have been so far, the probability that all future ones will be white is small. And in particular, if the number of future counters exceeds those that you've seen, then the probability is less than 1/2. So, Jeffreys thought this was horrendous. This was a terrible assault on the whole business of scientific inference. And he says, what Broad showed was that it was no justification, this is to say Laplace's approach, whatever, for attaching even a moderate probability to a general rule. It is necessary that it must have a moderate probability to start with. Thus, I may have seen 1 in 1,000 of the animals with feathers in England. On Laplace's theory, the probability of the proposition all animals with feathers have beaks would be about 1 in 1,000. This does not correspond to my state of belief or anybody else's. He thought there was something basically wrong, and he was going to fix it. And he fixed it. By the way, this is The Economist getting it wrong. The Economist in 2000 had an article saying, the new Bayesian era is upon us. And here they said, they talked about a newborn babe seeing the sun rise every day. Gradually, the initial belief that the sun is just as likely as not to rise each morning is modified to become a near certainty that the sun will always rise. So there we have The Economist. He's actually 82 years behind Charlie Broad on this particular one. They get wrong precisely the point that he was making. So, Jeffreys didn't do this on his own. In fact, he did it with Dorothy Rinch. Who was a philosopher who eventually went to America, and they did a paper together, and the conclusion they came up with, you needed to have a lump of probability on the scientific law being true. You couldn't smear simply anything you liked. You couldn't say every value was equally likely. You had to have lumps of probability on particular values being likely. This, by the way, is a picture of Dorothy Rinch. At least, it's a picture, I think. I found it on the internet, and it seems to suggest it was Dorothy Rinch. I don't know for sure. So, here's a simulation again. Here I show how this works. I'm going to do 2 particular approaches to hypothesis testing. One of them is what David Cox has called the dividing hypothesis. I believe it's possible that one of the two treatments would be better. I don't really care too much about them being equal anyway. I simply want to avoid claiming that what I think is the better treatment is really better when it is in fact worse. I want to avoid making an error of recommending to a patient that they take what I think is a better treatment when in fact it's worse. On the other hand, I don't really believe necessarily in the identity of treatments. On the other hand, what you could do is you could have a different sort of test. You could actually believe that 2 treatments were identical, and ironically, at the time that Cushning and Peebles were doing their work, it would have been possible to believe that 2 optical isomers could have absolutely identical effects, because certainly not very long before that, chemists had been astonished to discover that under some circumstances they didn't. These were 2 molecules which, to all intents and purposes, were indistinguishable. In the 2-dimensional space, writing them down on a sheet of paper, they would look the same. only if you could envisage them in 3 dimensions would they be different. The same atoms were involved, the same atoms were at the same positions. It was just some slight configuration that was different, and somehow, nevertheless, they could make a difference. And this eventually, the fact they did, led to the specific receptor theory of pharmacology, the idea that a molecule actually acted as a key in a lock on the cell and switched on something in the body. So, these 2 particular simulations here, what I'm doing is I'm working out how often I would get it wrong if I was simulating from these 2 particular models. What proportion of the occasions in which I claim there was an effect would there actually be no effect? And what you can see is that the Bayesian posterior distribution here, it actually tracks the p-value. There's some simulation error here perhaps, whereas if I use the Jeffreys approach, I get something radically different. It's the lump of probability that makes the difference, not here, certainly, switching from p-values to Bayesian prior distribution. Now, none of this is radical new. Everybody knows it, but for some reason, it's completely forgotten every time the debate takes place, and I don't understand why. So why the difference? The difference, I think, is fairly easy to understand. This is the likelihood. This is the probability as a function of the true difference delta, the probability of the result that we saw as a function of the difference between the 2 treatments. This is the value that the statistic has, and I've taken here a case where it will be just significant at the 5% level 2-sided, and it's a huge sample, so I can use the normal distribution, not students t, and the wonderful value that we all remember off by heart is 1.96. Similarly, we can all remember the value for a chi-square with 1 degree of freedom, 3.884, but 2 degrees of freedom, 5 point something, I forget. But anyway, it's one of those values we know, 1.96, that's the value here, and this is the likelihood. And now, let's imagine we have a dividing hypothesis. I'm interested in knowing whether the yellow area is what is true about the true effect, the true difference delta, or the blue one. This is the likelihood of the result under the parameter, and you can see that in this particular area here, it's fairly well supported, but it doesn't matter. Even when I'm out here well to the right, I can always find values here much further to the left which are not as well supported. In other words, the picture, if this is what I'm looking for, the picture is moderately encouraging that what I have got is I've got an effect. But now let's imagine I'm in the world of Jeffreys hypothesis testing. This is the alternative hypothesis, all of this, and so is this. All of that is the alternative hypothesis, and I now have an infinite jar of probabilities. I have a massive probability at 0. Every time I pull out a likelihood value here, then in that case, I can pull out one here. And now it turns out that many of the ones I'm looking at, not just in the wrong tail, but also in the right tail, all the values here, are actually less than the likelihood at this particular value here. And people like David Cahoon sometimes say, well, I start out with the probability that the null hypothesis is true of 0.5, which is surely not unreasonable. It's not so much the 0.5 of the null hypothesis, it's the exact mass on about around 0, or an accretion around 0, which is the problem. So, this is what I offer you as the real history. Scientists before Fisher were using tail area probabilities to calculate posterior probabilities. And this followed more than a century of work, interesting mathematical statistical work, largely grounded in Laplace. Fisher pointed out this interpretation was unsafe and offered a more conservative one. Jeffreys, influenced by Broad's criticism, actually I'm a bit uncertain pronouncing it Broad, it may well be his name was Broad, I don't know, but anyway, Broad's criticism was unsatisfied with the Laplacian framework, and he used a lump prior on probability on a point hypothesis being true. In actual fact, some wagon-makers recently, or Wagenmachers perhaps, I don't know, have claimed that Haldane in 1932 anticipated Jeffreys. But then again, I have to say, well, that might be right as regards some technical details, but Jeffreys and Rinch had already had the idea earlier than that anyway. It's Bayesian Jeffreys versus Bayesian Laplace that makes a dramatic difference, not frequentist Fisher versus Bayesian Laplace. So in summary, what I think is that the major disagreement is between p-values and Bayes. It's not between, p-values and Bayes. Or at least not Bayes using an uninformative prior distribution. It's between two Bayesian approaches, using uninformative prior distributions and using a highly informative one. This conflict is not going to go away by banning p-values, and if you have a look at the ASA statements of the American Statistical Association, felt it was necessary to put out a public statement on p-values. And as I pointed out last year, when we were talking about this, we had a RSS session on the ASA statement. People complained that the statement was actually wishy-washy. And I put it like this: if only the other 26 people involved could have agreed with me, we would have had something much more reasonable, but there we are. The conflict is not going to go away by banning p-values, and my lesson here, the point of view I have here, is there's really no automatic Bayesianism. You have to do it for real. So my tentative opinion is there may be a harmful culture of significance. I don't want to argue in favor of p-values as being a great way to look at data. They're one of a number of different ways that you look at them. They may be a signal that it's time to think a little bit if there's a rather unexpected result that comes up. Certainly 5% significance is a very, very moderate level of anything. Where you've got more structure, you can often do better. Here are some ideas. Using likelihood. Has problems with nuisance parameters, but nevertheless. Confidence distributions are another way of looking at things. Deborah Mayo has proposed severity, which is a way of thinking of p-values, not just conditioning on the boring null hypothesis, but conditioning on other values as well, a sort of p-value distribution. Point estimates and standard errors, and in fact, they're extremely useful for future research synthesizers, although the way the world is going, we're just going to be sharing data in the future. So pessimistically, sometimes I think whether there'll be any statistical analysis at all which is worth publishing, because everybody will have their own just using the data. However, we'll see. Or some of you will see. And also, of course, Bayes. So Bayes is good for personal decision-making. And there's the subjective Bayesian school, in which you might say Ramsey, De Finetti, Savage, Lindley, and more modern proponents rather like Anthony O'Hagan. Pragmatic compromisers, I could mention people like Jack Good, who I have done, George Box, and then also colleagues of mine when I was at Ciba Geigy back in the 1980s, Amy Racine, Andy Grieve, Hugo Fleuler, and Adrian Smith, who, a former president of the Royal Statistical Society, have a very nice paper that was a red paper in 1986 to the Royal Statistical Society pointing out how one could use Bayes practically. As an aid to thinking, Robert Matthews, whom I quoted right at the very beginning, he was the person with the bologna machine. He has a way of thinking about it like this. If you think this result is impressive, let's try and work out what your Bayesian prior distribution must have been to allow you to claim that. So we can then see whether this is a plausible thing to hold. And the conditional Bayesian approach of Spiegelhalter, Friedman, and Palmer, there was a paper read to the Royal Statistical Society in 1984, Bayesian approaches to randomized trials, BART, which also advocates using different prior distributions and seeing how the results hold up. So you could have an uninformative prior, a skeptical prior, an enthusiastic prior, and so forth. In that paper, I note there is a very, very slight reference of using a lump probability, such as Jeffrey's used, but on the whole, that's not, I think, but David could certainly correct me over dinner. I don't think there's a particularly an enthusiastic espousal of that in that paper. Not so good, in my opinion, Bayesian significance tests. I'm not particularly enamored. Bayes factors, I'm not a great fan. P-value is modified to behave like Bayesian tests. I'm certainly not a fan. And Andy Grieve said, well, okay, Stephen, that's fine, but how about this awful thing of Bayesian approaches modified just to make them behave like p-values? That's also equally bad, so both sides are guilty in that particular way. Speaking of BART, by the way, I was very much struck by the time when I was at Ciba Geigy and David first unveiled his approach to, in particular, sequential monitoring and various matters in clinical trials, then Bart Simpson was just making an impact on television, and David often used to bring up cartoon figures of Bart, and I think maybe he was slightly influenced by that in choosing Bayesian approaches to randomized trials. So speaking of Bart, however, Bart has been replaced by somebody else in the Simpson pantheon. As everybody now knows, the true hero of The Simpsons is not Bart, it is in fact Homer. And you can see what he's holding. This longer stands between you and a drink. Thank you very much, ladies and gentlemen.